Okay, so have you ever wondered if maybe computers could help us, well, think better?
Like, think better about big philosophical questions.
Exactly, things like knowledge, how society works, or even like what it all means, existence and stuff.
Yeah.
It sounds kind of far out, but there's actually this whole growing area called computational philosophy.
And it's not as new as you might think. I mean, go back a few centuries and you have Leibniz. He wasn't just building calculators, he had this bigger vision for how computation could change how we think.
So today, on the deep dive, we're going deep into computational philosophy, and we're using the Stanford Encyclopedia of Philosophy as our main guide. But hold on, it's not about the philosophy of computers, like AI ethics.
Right, it's not about that.
It's philosophy using computers.
That's the key difference.
So it's about using these computational tools, techniques, to explore and really get a deeper understanding of these classic philosophical questions. And for anyone who's like, I want to understand these big ideas, but maybe in a faster, more efficient way, well, computational philosophy, it offers this whole new way of looking at things.
And it leads to some aha moments, for sure.
Definitely. So we'll be tracing back some of the historical roots and then diving into how it's being applied today across, all these different areas of philosophy. And our mission for this deep dive is to explore how, these computational methods are changing how we do philosophy and what kind of new understandings are they revealing in areas that, traditionally were approached through just pure thought and argument.
Right, like pure reason.
Yeah, exactly.
So you mentioned the historical origins. Let's go back there, back to Leibniz.
Back in time.
He was a fascinating figure. He wasn't just a philosopher, he was a mathematician. And he really was a pioneer in computation. He designed calculating machines, the Pascaline, and then his own stepped reckoner with this thing called the Leibniz wheel. These were incredibly advanced for their time. They could perform all four basic arithmetic operations.
So addition, subtraction, multiplication, and division.
All of them, yeah.
Wow.
And, a working model of his stepped reckoner was actually rediscovered centuries later.
Oh, wow.
So that gives you a sense of just how ahead of his time he was.
Right. It's like finding a blueprint from like way back when.
Exactly, and realizing it actually works. But his ambition wasn't limited to just, crunching numbers. He had this broader vision, what he called the art of combinations.
So it wasn't just about doing calculations.
Not at all. It was about using formal methods to analyze complex ideas, but also to generate new ones. He saw it as this kind of universal key to problem solving.
Oh, interesting.
Yeah, he called it the mother of inventions.
Wow.
A method that could potentially lead to the discovery of all things.
So like a framework for knowledge and discovery. That's a good way to put it.
And he thought it could be applied across all sorts of fields: logic, law, medicine, even physics.
That's ambitious.
Hugely. And at the heart of it was his idea of a perfect language of pure concepts.
Okay, what does that even mean?
So the idea was, if you could express philosophical concepts and arguments in this precise, formalized language, you could, in theory, mechanize the very process of reasoning.
So like program logic into a machine.
That's the essence of it. Gray, in 2016, called it the general mechanization of reason itself.
That's pretty mind-blowing.
It is.
And the encyclopedia mentions earlier attempts at this too, like Raymond Lull.
Right?
And even that funny part in Gulliver's travels with the machine that makes books.
Oh, right, the word generating contraction. But what's interesting is that Leibniz's core idea that we can use computational methods to address these big philosophical questions, that's what connects all the way to the computational philosophy we see today.
Okay, so fast forward to today. We're not using one single computational method to answer everything. It's more like a whole bunch of different approaches are being used to tackle specific philosophical questions.
Exactly. And some areas of philosophy have proven really fertile ground for these new models and techniques. One that's quite accessible, I think, is the use of agent-based modeling, particularly in social epistemology.
Okay, so let's break that down. Social epistemology, that's the study of knowledge and belief within social groups, right?
Right. It's not just individual knowledge, it's how knowledge is acquired and validated within groups.
So instead of just asking, how do I know something? We're asking, how does a group, like a team of scientists or even the jury, how do they come to know something?
Precisely. Like, how do they decide what's true? How do they share information?
And this is where computers become really useful, right, to model these complex social dynamics.
Absolutely. Think of it like this. You create these simulated individuals called agents in a computer program, and you give them certain rules for how they interact and how they change their beliefs based on what others in the group believe. Then you run the simulation, and you observe how the beliefs in this little simulated society change over time.
So you can test out different theories about how people form beliefs.
Exactly. And you can see how different like how open people are to changing their minds or who they listen to, how those factors affect the overall spread of beliefs.
Yeah, that's pretty cool.
And one of the models they mention in the encyclopedia is the Hegselman-Krauss model.
Okay, so what's special about that one?
It's actually a very simple model, which makes it quite elegant. Imagine you represent beliefs or opinions as numbers, like on a scale from 0 to 1.
Okay.
And you have a bunch of these simulated agents, each with their initial belief. Then they update their belief based on the average of the beliefs of those who are close enough to them in opinion.
Okay, close enough, but how do you define that?
That's the key. They use a parameter called epsilon to represent this threshold of closeness. And this epsilon value has a huge impact on what happens in the simulation.
So if epsilon is small, people only listen to those who already agree with them.
Pretty much, yeah. And that leads to fragmentation, where the group splinters into separate clusters with very different beliefs. But if you increase epsilon, people become more open to considering opinions that are further away from their own.
And then what happens?
Then you start to see polarization, where you end up with two distinct opposing camps. But if you keep increasing epsilon, if people become open enough to considering all viewpoints, eventually everyone converges on a single opinion.
So it goes from fragmentation to polarization to consensus.
Exactly.
Huh.
And what this model shows is that something as simple as who you're willing to listen to can have a huge impact on the overall landscape of beliefs.
It's like that saying, you are the average of the 5 people you spend the most time with.
Something like that, yeah.
But of course, real life is more complicated than that. The encyclopedia mentions other models that build on this basic idea, like Tichuan's work where influence is more gradual.
Right, so instead of a hard cutoff for who influences you, it's more like a gradient. The closer someone is to you in opinion, the more they influence you.
Makes sense. And they also talk about stubborn individuals, those who are less likely to change their minds.
Oh, yes, those. And it turns out that even a small number of stubborn individuals can really change the dynamics of the group.
It's like those people who are just set in their ways, no matter what you say.
Exactly. And then there are more complex models, like Olson and Andrews Laputa, which uses Bayesian networks and the concept of trust.
Okay, Bayesian networks, those are like flowcharts, where arrows show how different factors influence each other, right?
That's a good way to visualize it. And each connection has a number representing how strong that influence is.
So you can model how beliefs change based on new evidence and also who you trust as a source of information.
Exactly. And what's interesting about this is that it allows you to explore the rationality of polarization.
So people can end up in very different camps, even if they're all trying to be rational.
That's the surprising finding. It challenges the assumption that polarization is always a sign of irrationality or bias.
That's pretty thought-provoking.
It is. And it's not just about who you trust. There's also the issue of how we evaluate evidence. Kevin Dorst has done some interesting work suggesting that even fully rational agents, if they selectively scrutinize evidence that goes against their beliefs, can end up becoming more polarized.
So even if you're being logical, you can still end up in an echo chamber.
It's a real possibility. And this connects back to some earlier work on cultural dissemination by Robert Axelrod, who used cellular automata models.
Cellular automata, those are those grids where each cell follows a simple rule, and you get these complex patterns emerging, right?
That's it. And Axelrod used them to model how cultures spread and change over time.
Okay, so how does that work?
Imagine you have this grid, and each cell represents an individual with certain cultural traits, like their favorite food or their preferred style of music. They interact with their neighbors based on how similar they are, and if they interact, one might adopt a trait from the other.
So people become more similar to those around them.
Exactly. And what's surprising is that while you see local convergence, meaning neighbors becoming more alike, you often end up with global polarization.
Wait, though people become more similar locally, but more different globally.
Yes, that's the counterintuitive part. You end up with distinct regions with very different cultures that no longer interact with each other.
Wow, it's like those cultural divides we see in the real world.
It is, and what Axelrod found is that the number of these cultural regions depends on the number of traits and features involved. The more traits, the more isolated regions you tend to get.
It's like the more diverse a culture is, the more likely it is to fragment.
In a way, yes. And the encyclopedia makes an important point here, which is that computational modeling forces us to be very precise about what we mean by terms like polarization. It's not a single, uniform concept.
So different models might capture different aspects of it.
Exactly. Bramson and his colleagues have really emphasized this. We need to be clear about what we're measuring and how, and that's one of the real strengths of computational philosophy.
It forces you to be rigorous.
Absolutely.
So we've talked about models where beliefs and cultural traits kind of spread through a population. But what about the role of arguments and reasons?
Ah, that's where Gregor Betz's model of dialectical structures comes in. It tries to model how arguments, with their supporting and attacking relations, influence what we believe.
Okay, so instead of just blindly adopting beliefs, people are actually considering arguments.
Exactly. He represents statements and their negations as numerical values and arguments as sets of these statements. And then he maps out how different positions or truth value assignments relate to each other within this whole network of arguments.
So it's like mapping out a debate.
That's a good analogy. And then he runs simulations to see how beliefs evolve as arguments are introduced and debated.
And what does he find?
What's interesting is that he finds that what he calls controversial argumentation, where arguments are specifically brought in to support your own position or to attack someone else's position, that kind of argumentation can actually be good for both reaching consensus and getting closer to the truth.
Really? So arguing with each other can actually be helpful.
In the long run, it seems so. Of course, any individual debate can go all sorts of ways. But on average, engaging directly with arguments seems to be beneficial.
That's good news for us, I guess, since we're always debating things.
It is indeed.
So we've seen how computational philosophy is giving us all these insights into belief change and social dynamics. Now let's switch gears a bit and talk about the philosophy of science. How are computational methods being used there?
There are two main ways, actually. First, as models of scientific theories themselves, and second, as models of the social interactions that happen within science.
Okay, so let's start with models of scientific theories. The encyclopedia mentions Paul Thygard's ECHO program. What's that all about?
ECHO is a connectionist program that tries to model how we evaluate different scientific explanations. It creates these networks of nodes where each node represents a hypothesis or a piece of evidence.
Yeah.
And the links between the nodes can be either excitatory, meaning they support each other, or inhibitory, meaning they conflict.
So if one hypothesis explains a lot of evidence, those would have excitatory links.
Exactly. And if two hypotheses are competing to explain the same thing, they'd have inhibitory links. Then the program runs through cycles, strengthening the nodes that are consistent and weakening those that aren't.
So it's like a process of sorting out which explanations fit best with the evidence.
That's the basic idea, and Thygard argues that the hypotheses with the highest activation at the end are the ones that exhibit the greatest explanatory coherence.
So the ones that make the most sense overall.
Precisely. And he's even used ECHO to model historical cases of scientific revolutions, like the shift from phlogiston theory to oxygen theory.
Wow. So it can show how scientific understanding changes over time.
That's the goal. And then, of course, there's the huge influence of Bayesian networks in philosophy of science.
Right. We talked about those earlier.
They've become really central. Essentially, they're directed acyclic graphs where each node represents a variable, which could be a probability or a degree of belief, and the arrows represent conditional probabilities.
So you can model how the probability of a hypothesis changes as you get new evidence.
Exactly. And the power of Bayesian networks is that they can handle very complex relationships between many different variables. And because these calculations can get really complex, computers are essential for working with them.
They're like a powerful tool for reasoning about uncertainty.
That's a good way to put it. And they're used for all sorts of things in philosophy of science, like understanding explanation, confirmation, and even how competing hypotheses stack up against each other.
And beyond philosophy of science, they're used all over in AI.
Oh, absolutely, especially for causal inference.
So Bayesian networks are kind of a big deal.
They are indeed. Now, the encyclopedia also talks about network models of scientific communication.
So how scientists talk to each other and share their findings.
Exactly. And the big question is, what kind of communication structure is best for science to make progress?
You'd think more communication is always better, right?
You would, but some of the computational modeling suggests that's not always the case. It turns out that sometimes a little bit of distance and independent exploration can actually be good for science.
Really? That's counterintuitive.
It is, but there's a logic to it.
Okay, I'm curious, what kind of models are they using to study this?
Many of them use agent-based models where you have these simulated scientists making choices about research methods, collecting data, and then sharing their results with others in their network. And Kevin Zollman has done some really important work in this area, looking at how different network structures affect how quickly and accurately a scientific community converges on the truth.
So, like comparing a fully connected network where everyone talks to everyone else versus a more distributed network where communication is more limited.
Exactly. And what he's found is that the fully connected network, what you might call the Internet of Science, isn't always the best.
Yeah.
Sometimes these more distributed networks, even though they might be slower, can be more effective for finding the truth.
Why is that?
The idea is that in a fully connected network, scientists might converge on a popular but wrong idea too quickly. Whereas in a distributed network, there's more room for independent exploration and for someone to stumble upon the right answer, even if it takes a bit longer.
So it's like having too much information too soon can be a bad thing.
It can lead to premature consensus. And these models have been extended to look at things like biased information sources and propagandists.
So how misinformation spreads in science.
Exactly. And it turns out that highly connected networks can be vulnerable to that kind of manipulation.
That's a bit worrying.
It is something to be aware of.
Now, the encyclopedia also mentions this concept of an epistemic landscape. What is that exactly?
It's a way of visualizing the space of possible solutions to a scientific problem. Think of it like a real landscape with mountains and valleys. The height at any point represents how good a particular solution is.
So the peaks are the best solutions.
That's the idea. And scientists are like explorers trying to find the highest peaks.
And they use these landscapes to model how different communication networks affect this search for the best solutions.
Exactly. And what they find is that the structure of the landscape matters a lot. On smooth landscapes with one clear peak, it doesn't matter too much how scientists are connected.
Because they'll all find the peak eventually.
Yeah. But on more complex landscapes with lots of local peaks, what they call needle in a haystack landscapes, distributed networks can be better at finding the true highest peak.
So limited communication can actually help in those cases.
It can lead to more thorough exploration, and that's another key insight from this work. Now, the second big area in computational philosophy of science is looking at the effects of division of labor and diversity.
So how different kinds of thinkers or different approaches contribute to science.
Exactly. And one of the early models here was by Weisberg and Muldoon, who looked at followers and mavericks.
So followers build on existing work and mavericks go off in new directions.
That's the basic distinction. And their initial findings suggested that having both followers and mavericks was good for science. But their model was criticized for some errors in how it was implemented.
So it's not clear-cut whether mavericks are always helpful.
Right, it depends on how you define them and how the model works. But the encyclopedia highlights the work of Hong and Page as a more robust model for studying diversity.
Okay, what did they do?
They modeled scientists exploring a random landscape using simple rules of thumb called heuristics. And they compared groups of individuals who are best at finding high points on the landscape with groups of individuals using random heuristics.
So some were really good at solving problems, and others were just trying random things.
That's a simplified way of putting it, yes. And what they found, which is quite surprising, is that the groups with random heuristics often did better than the groups of the best individuals.
Really. So diversity of approaches trumps individual ability.
That's what they called it, the diversity trumps ability result. It suggests that having a diverse set of problem-solving approaches is more important than just having a bunch of really smart people who all think alike.
That's a powerful idea.
It is. And again, the structure of the landscape matters. This result holds up well on complex landscapes, but not so much on simple ones.
So it's all about context.
Exactly.
Now let's move on to ethics and social political philosophy. How are computational methods being used to study those big questions about how we should live together?
Well, one central theme in both ethics and social and political philosophy is the problem of cooperation.
Right. How can people cooperate if they're all self-interested? That's something that thinkers like Sidgwick and Hobbes struggled with.
Exactly. And game theory has been a really useful tool for studying this. And computational methods allow us to take those game theoretic models even further.
The classic example is the prisoner's dilemma, right? Where it seems like the rational choice for each individual is to betray the other, even though that leads to a worse outcome for both of them.
Exactly. And computation models have helped us explore different mechanisms that might support the evolution of cooperation.
Like repeated interactions.
Yes, that's one. If the game is played over and over, players can learn to cooperate.
What else?
Kin selection, where cooperation is favored among relatives, and even spatial arrangements where players interact more with their neighbors.
So the structure of the interactions matters.
A lot, yes. Robert Axelrod's famous tournaments with the iterated prisoner's dilemma were a great example of this.
That's where different strategies played against each other in a computer simulation.
That's it. And the surprising finding was that a very simple strategy called tit for tat did really well.
What's tit for tat?
It's basically cooperate on the first move and then do whatever your opponent did on the previous move.
So cooperate if they cooperated, defect if they defected.
Exactly. And when you introduce spatial interactions, as in those cellular automata models we talked about earlier, you see even more interesting patterns emerging.
With clusters of cooperators able to survive and spread.
Precisely. And researchers like Nowak and Sigmund have even looked at the role of noisy signals and imperfect information.
So what happens when players don't have perfect knowledge of each other's actions?
Right. And they found that strategies like generous tit for tat, which sometimes cooperates even after a defection, can be surprisingly successful.
So a little bit of forgiveness can go a long way.
It seems so. And these game theoretic models are now being applied to much broader questions of social justice and political philosophy.
Like looking at the causes of inequality.
Exactly. Chris Bruner's work, for instance, shows how even seemingly neutral interaction structures can systematically disadvantage minorities.
Wow, so even the rules of the game can be biased.
That's the troubling finding. And there's a lot of exciting work being done using these tools to explore issues of intersectional disadvantage and power dynamics.
So it's not just about abstract games anymore. It's about real-world issues.
Absolutely. And the encyclopedia also talks about computational models of democracy.
How do you even model something as complex as democracy?
Well, there's the classic Condorcet jury theorem, which shows that in a simple majority voting system, the probability of the majority being right increases as the number of voters increases, as long as each voter has a better than even chance of being right.
So the wisdom of the crowd.
In a way, yes, but computational models let us explore more complex scenarios, like hierarchical representation and the effects of deliberation.
And what do they find?
Interestingly, some simulations using models of deliberation suggest that representative structures, like having elected officials instead of everyone voting on everything, might not actually be a bad thing for deliberation.
So maybe representative democracy isn't so bad after all. Yeah.
It might not be as inefficient as some people think, and the combination of big data and computational philosophy has a lot of potential here for understanding how real-world democracies work.
It's like we're starting to see social outcomes not just as the sum of individual actions, but as emergent phenomena arising from complex interactions.
Exactly. And that's where the lens of complex systems theory becomes really useful.
Right, the idea that the whole is more than the sum of its parts.
Exactly. And the classic example here is Schelling's model of residential segregation.
Ah, the one with the pennies and dimes.
That's the one. It shows how even mild preferences for living near people of your own group can lead to large-scale segregation.
It's kind of mind-blowing that such simple rules can lead to such complex patterns.
It is. And while the specific assumptions of Schelling's model have been debated, the core insight about how individual choices can aggregate into large-scale social patterns is still really powerful.
It's like those unintended consequences we talked about earlier.
Exactly. And computational models can help us understand those.
Now, the encyclopedia shifts gears a bit and talks about a different kind of computational philosophy, one that's less about simulation and more about using computers to mechanize and extend philosophical argument itself.
Right. So instead of just modeling philosophical ideas, it's about using computers to actually do philosophy in a way.
Okay, I'm intrigued. What kind of things are they doing?
Well, it goes back to Leibniz's vision of a mechanized logic.
Right, that perfect language of pure concepts.
Exactly. But the real breakthrough came with the development of automated theorem provers.
Theorem provers.
They're basically computer programs that can prove logical theorems.
Like actually prove things.
Yes, they can.
Wow.
And one of the early examples was Newell and Simon's logic theorist, which could prove theorems from Principia Mathematica.
Principia Mathematica, that's the massive book on logic by Whitehead and Russell.
That's the one. And Russell himself was apparently quite impressed by the program.
That's high praise.
It is. So these programs, they're given a set of logical rules and a statement to prove, and they systematically try different combinations of those rules until they arrive at a proof.
It's like a computer doing the work of a logician.
That's a good way to put it. And these programs have become incredibly powerful. There are ones for all sorts of logics, including higher-order logics that are used in philosophy.
So they're not just limited to basic propositional logic.
No, not at all. They can handle modal logic, deonic logic, epistemic logic, all sorts of complex logics.
And they've been used to solve actual problems that logicians were struggling with.
Oh, yes. There are examples of conjectures in Robbins algebra that were proven by automated theorem provers, and they've been used to find the shortest axiomatizations for certain modal logics.
So they're not just a toy, they're a real research tool.
Absolutely. And the applications go beyond just pure logic. They're being used in deontic logic to try to formalize ethical reasoning.
So using computers to think about right and wrong.
In a very precise way, yes. And then there's the really fascinating application to metaphysics and philosophy of religion.
Okay, how does that work?
Well, Ed Zalta and his collaborators have used theorem provers to explore concepts like possible worlds and Plato's theory of forms.
So very abstract metaphysical ideas.
Exactly. And they've also been used to analyze the ontological argument for the existence of God.
That's the one that tries to prove God's existence through logic alone.
That's the one. And researchers have used theorem provers to analyze reversions of that argument, including the ones by Spinoza, Anselm, and even Gödel.
Gödel, the famous mathematician.
The same one. And what's amazing is that they've actually found inconsistencies in some of these classic arguments using theorem provers.
So the computer is finding flaws in the logic.
Exactly. It's like having a superpowered logic checker.
That's pretty incredible.
It is. And it shows how computational philosophy is opening up whole new ways of engaging with these fundamental philosophical questions.
So it's not just about simulation. It's about using computers to do philosophy itself.
That's a good way to put it.
Now, the encyclopedia also mentions the connection between AI and philosophy of mind. How do those two fields relate to all of this?
Well, AI has always been closely tied to philosophy of mind. While a lot of AI research focuses on practical applications, some researchers see it as a way to understand the nature of intelligence and thinking itself.
So building AI could help us understand our own minds better.
That's the hope. John Pollock's Oscar project is a good example of this. He was building an AI program specifically to model human rationality.
So he saw AI as a way to test theories about how we think.
Exactly. And his program, Oscar, was designed to handle things like defeasible reasoning and philosophical paradoxes.
So it was grappling with some pretty sophisticated philosophical problems.
It was. And while AI isn't just a branch of philosophy of mind, it can definitely inform our understanding of how our minds work.
It's a two-way street then.
Absolutely.
So this has been a pretty mind-expanding overview of computational philosophy.
It's a big field.
It is. Now the big question is, how do we evaluate all of this? What are the limitations? What are the criticisms?
Well, one common criticism, especially of the simulation-based work, is that you can basically prove anything with the simulation if you just tweak the parameters the right way.
Right, like you could just make the simulation do whatever you want.
That's the worry. And it's a valid one.
So how do computational philosophers respond to that?
Their response is that it's similar to how we evaluate any argument, whether it's a logical argument or a scientific experiment. Just because you can make a simulation do something doesn't mean that it's a good model of reality.
So it's about the quality of the model, the assumptions it makes, the way it's built.
Exactly. And anyone who's actually built these models knows that it's not easy to make them do something interesting or meaningful. It takes a lot of work to get them to produce robust, consistent results.
And a lot of the time, they fail.
Right.
Right.
Yes. Simulations fail all the time. And that's actually a good thing because it shows us where our initial ideas were wrong or where the model needs to be improved.
So failure is part of the process.
It's essential.
The encyclopedia talks about verification and validation. What do those mean in this context?
Verification is about making sure that the model actually does what it's supposed to do. So if you're modeling a particular theory of belief change, you need to verify that your program actually implements that theory correctly.
Makes sense.
Validation, on the other hand, is about making sure that the model actually reflects the real world.
So it's not just internally consistent, it's also externally valid.
Exactly. And that's a much harder thing to do.
Because the real world is messy and complex.
It is. And critics often point out that models are too simple, that they leave out important details.
And they're right, in a way.
They are. But the goal of modeling isn't to perfectly replicate reality. It's to capture the relevant features for the question you're asking.
Like that Borges quote about the map that's the same size as the territory.
Exactly. A map that's perfectly accurate is useless.
Because it's just as complicated as the real thing.
Precisely. And the encyclopedia also talks about robustness testing, which is about seeing how sensitive a model's results are to changes in its parameters.
So if you tweak the settings a little bit, do the results stay the same?
Right. And if the results only hold within a very narrow range of parameters, then we should be cautious about generalizing from them.
It's like a reality check for the model.
It is. And what's encouraging is that a lot of this critical evaluation is happening within computational philosophy itself. Researchers are constantly testing and refining each other's models.